Cool. All right. So, hey, we're finally out of chapter 4. So you'll see that we're going to move a little more quickly now because we've kind of learned the big skills. And now it's just a matter of applying them. And section 5 is pretty short. The whole chapter is pretty short. But it's the first one we're doing is 5.1. We're going to be solving differential equations, which we've already kind of looked at differential equations, but these are a special type because they're not always functions of x to begin with. They could be functions of x and y, or just y, or we could still have some that are just functions of x. So we call them separable differential equations, and I'll show you what that means. So just to review, remember, a differential equation is nothing more than an equation, right? Surprise, that has a derivative in it. It could be a first derivative, second derivative, third derivative. And solving the differential equation essentially means getting all the way back to the original function. That is, find the original function that satisfies that equation. Here's some examples right here that we've seen. dy dx equals that. We call that a first order differential equation because it's a first derivative. Okay, a first order differential equation. Now this one's easy to solve because it's already a function of x on the right hand side. So these are the ones that we've already seen, right? So if we take the antiderivative of both sides, this becomes y on this side, and this side, of course, becomes 3/4 x to the 4th plus 2x squared plus c. We've already done those. So that's first order. Here's another first order differential equation, right? It's a first derivative. It's equal to sign. Solving it means getting back to f. What's the solution to this one? What is f equal to? What kind of cosine? Negative cosine plus c. Okay, so that's another first order. This one is the second order differential equation because it is a second derivative. So solving this one means getting back to h, the very first function. So you'd have to do it twice, okay? And this one, again, should be pretty easy because it's a function of the single variable. Instead of x this time, it's t. So you'll see in this section now, we don't always have to have just the independent variable on the right-hand side. We can have dependent variables or combinations thereof. All right, so a separable differential equation, moving down here then, is one for which all of the dx's and x's and the dy's and y's, all of the x's and dx's and all of the y's and dy's can be separated. Okay, we're going to start with a differential equation that looks something like this. You're going to have a first derivative, and it's going to be equal to not just a function of x, but it might be equal to a function of y or any combination thereof. But it has to be a product of x factors and y factors. Okay, and of course, that could also be a quotient. So we know that dividing is just multiplying by the reciprocal. So it could be like f of x times g of y, or f of x divided by g of y, I should say, or any combination thereof. But it has to come from multiplication or division. So our first task when we have a function like this, that's a differential equation, before I can solve for y, since I might have y's on the right-hand side for the first time, is to separate it. So our goal is to separate the variables so that on the right-hand side, we have not just our dy's, but we have our y's and our dy's. And on the right side, we have our x's and dx's, okay? Let me show you what I mean here. Here's example 1. The graph of several solutions to this differential equation, dy dx equals x squared divided by y squared. So for the first time, we've seen a derivative that is not just a function of x, okay? It's shown over here. So these are all general solutions. Now notice these don't look like they're just vertically shifted from each other, do they? Okay, whenever they're just functions of x, we integrate. The plus c is just a vertical shift. So all of your general solutions are going to look like they're just shifted up and down from each other. But these don't look that way. And the reason they don't look that way is because it's a function of both x and y. So these are particular solutions. If you hop on any one of these graphs, these are called particular solutions. And you take them all together and it kind of looks like an onion bulb, right? Something like that. I don't know. So here's what we're going to do. We're going to first solve the differential equation and find the general solution, okay? The general solution. The general solution is the one that has C in it. So let's come down here and let's rewrite it so that we can work with it. Okay, so remember that your independent variable is x, right? You can see that because it's the derivative of y with respect to x. And everything we've seen so far has only been in terms of x. But now because we have this dependent variable on the right side, we have to separate it. And again, the algebraic process in separating the variables, x's and dx's on the right side, y's and dy's on the left, it has to come from either multiplication or division. Okay, so in this case, what could I do? Well, I could simply cross multiply, right? That's all it takes in this case is to cross multiply. So if I multiply along this diagonal, I get y squared dy. And if I multiply on that diagonal, I get x squared dx. Okay. That was enough to do it, right? Does that work? Yeah, because now notice on my left side, I have all my dependent variables, and on my right side, I have all my independent variables. So this would earn a check on a free response, simply showing it. Now, if you don't show that step and you somehow manage to get the right answer, you don't get any checks at all. This is kind of like a, giant fork in the road, right? If you don't show this step, you might as well not proceed on a free response because you're not going to get any credit after that, even if you somehow come up with the right answer. Now, of course, these are factors, so it could have been dy times y squared, dx times x squared, but we want to make sure that we get in the habit of putting your dy's as the right bookend, your dx's at the right bookend, and putting your y's on the left is where we're used to having them. So this is the separation of the variables. Now, once you separate the variables, and you can do it on the same line here. Now to solve, we're going to not take the derivative of both sides, but we're going to take the integral of both sides, okay? And that's a separate step, but you can go ahead. They're kind of tall and slender, right? So you can kind of sneak them in there on the same line. All right, so now notice why that's important. By separating the variables, I have my integral of y squared with respect to y, and now the integral of x squared with respect to x. So now it just turns into two problems. Yeah, 2 and 1. On the left side, the antiderivative is not just y anymore. So what is the antiderivative of y squared with respect to y? 1/3 y cubed. Yeah, now I'm going to put a plus c sub 1 here, because technically we need a plus c as soon as we take the antiderivative. But I'm putting an asterisk above it because you're going to see, just like when we have a definite integral, we don't need to show it because it cancels out. You're not going to have to show it on the left side where the dependent variable is, because we're going to just collect everything on the right side anyway. In the end, we still want to end up with y equals some function, okay? And then on this side, we get 1/3 x cubed plus, I'll put c sub 2. Now, if this were a free response, you would probably get one check for both antiderivatives because it's pretty much the same, and you'd get a one check for putting a plus c. So that's already worth 2 checks. And sometimes that line is worth 3 checks. If the left side and right side are completely different and it's like 2 separate rules of integration, you could actually get an antiderivative check each time. All right, so once you do this, the calculus is over. In fact, the calculus was here just one line. That's it. We did some algebra to separate the variables. We cross multiplied. We set up the table for the calculus, and then we BOTC'd. And now the rest of the problem is just algebra again. Okay, so once we separated the variables, I'll just write it on this line. That's what we did over here. And then we BOTC'd. I'll just put that right here. We BOTC'd. We busted out the calculus. I guess it would be not BOTC'd, it would be BOTC. I don't like that better. Mother-in-law's mothers-in-law. Yeah, it doesn't matter. We integrated. How about that? We integrated. Okay, we integrated. And now all that's left is to solve for y. Solve for y. So the first thing we're going to do to solve for y is get rid of this constant. So I'm going to subtract c sub 1 from both sides. And I get 1/3 x cubed plus c sub 2 minus c sub 1. Now, yes, very good. That's the whole point here. An unknown constant minus an unknown constant is another unknown constant. So I've already called c the ShamWow c. Okay, this is important. C can absorb constants. It can absorb constants either when they're added to it, like in this case, I have one constant added to another constant. When you're multiplied by it, divided by it, they can absorb constants until you get y equals. In other words, until you get to the general solution. All right. But after that, then it's locked in place. So yes, I will call C sub 2 minus C sub 1. I'm going to call it new and improved C. Okay. Now this is typically what our next line is going to be. You're not going to be penalized if you don't show the plus C on the left-hand side where the dependent variable is, right? Because we know that it's going to always be combined on the right-hand side, which is where everything's going to end up anyway. Okay, so you don't have to show it. So in the future, integrate the dependent variable side, integrate the deep independent variable side, or do the y's, then do the x's and put plus just C on the right-hand side with the x's. And that'll get you a check right there. Okay. So I just wanted to show it to you one time. I mean, you're welcome to put C sub 1 and C sub 2, but it's just more work. Okay. All right. So now, algebraically, how do I solve for y cubed first? Multiply everything through by what? 3. So if I multiply everything through by 3, I'm going to get y cubed equals x cubed plus 3 times c, right? 3 times c. What's 3 times an unknown constant? An unknown constant. And this is where we say sham wow. Sham wow c. Okay. Same thing over here. C sub 2 minus C sub 1. That was sham wow c. The C can absorb unknown constants or known constants, either one, that are multiplied, added, subtracted to it on your way towards solving for y. And now all I have to do to solve for y is take the what of both sides? Cube root. Okay. Now notice this plus C is still just added on at the end, which is like a vertical shift. But when I take the cube root of both sides, guess where that plus C ends up? Inside, under the radical. And that is no longer just a vertical shift, right? You can't take this, you don't take these cube root of both terms. That doesn't work. It has to be the whole thing, right? The square root of a plus b is not equal to the square root of a plus the square root of b. Doesn't work that way, right? Because they're terms. So when you take the cube root, it's not just the cube root of x plus the cube root of c. It's the cube root of the whole quantity. And c is now inside. So this is typically what happens when we have a separable differential equation, because we have a derivative equals something that's not just plain old x's. The plus c has to appear right away. You can't just do all the algebra and then just add plus c at the end. The plus c has to appear right away because it has to be treated like a number. It can absorb unknown things, but it has to be treated as a number. And it'll possibly change locations on your way to solving for y. Okay, like in this case, it went under the radical. And that's why these solutions here don't just look like they're vertical shifts of each other. Okay, so this right here would be the general solution. Let me just write that out here. This would be the general solution. So that would earn another check. So it's kind of nice to notice that even though I couldn't really solve dy dx at the top explicitly for just a function of x, I can solve the general solution for y as a function of x. Okay. All right. So what I want to do now is verify the following particular solutions. These are all particular solutions. And we can color code stuff. So let me use red here. I'm going to first draw it. When we do slope fields, or if you're at Landon's slope field teach/review, you realize that this kind of looks like a slope field, kind of, but it's really just a graph of the general solutions, which is kind of what a slope field is. Let's go ahead and draw the particular solution that passes through the point 0, 2. That's what that means. The particular solution passes through the point 0, 2. So where is 0, 2? This is 0, 2 right there. Okay. So now I want the equation of this. Okay, that would be the particular solution that passes through the point 0, 2. Well, that looks like it's a function of x, right? It passes the vertical line test. Yeah, so if I want to find the equation of that, all I have to do is go to my general solution and plug in the particular point, just like we did in the past, right? So we do have to show that we're plugging it in. So you can either say at the point 0, 2, colon, or you could say for y of 0 equaling 2, either one. It gave it to us kind of as the y of 0 equals 2. So whatever you want to do. And let's go ahead and I'm going to rewrite this. Y equals the cube root of x cubed plus c. Okay, so that's still the particular solution. So once I plug in, here's what we get. We get 2 equals the cube root of 0 cubed plus c. And then we just solve for c. So we get 2 equals the cube root of c. And now how do I solve? This is where it doesn't get absorbed, okay? C is now treated as a constant in that final general form. So you might say, hey, the cube root of an unknown constant is just an unknown constant. You can't do that, all right? At this point, yeah, C is super saturated. It can't absorb anymore, okay? It must stay as C at this point. Can't absorb anymore. No more ShamWell C. But at any point along your way towards solving, you can. All right. So now how will I solve for C? How do you undo taking the cube root of something? Cube both sides. So you get 2 cubed, which is 8. All right. So once we find C, and you're going to get a point for using the particular solution. Now we're going to say so or therefore, and now we just plug it back in. So y equals the cube root of x cubed plus 8. And notice again that 8 is under the radical, Isn't that kind of cool? Yeah, crazy cool. Now if you don't have to get it and get a calculator. I wanted to show you that equation that we just came up with will give us that graph. Let me just reload my ROM here. Figure out a solution to the Ukrainian-Russo conflict while I load my ROM. Okay, yeah, there we go. All right, so here we go. I'm gonna graph it and just show you that it works. So I'm gonna go to y equals, and I'm going to type in the cube root, which the way I type it in, remember, is parentheses. Oops, too many. Parentheses x caret 3 plus 8, close parentheses, all to the 1/3 power. That's the easiest way to type it in. Now, don't just hit zoom 6 because we have a nice little graph here already. Let's graph it in the same window. -3 to 3, count by ones. -3 to 3, count by ones. Now, here we go. Oh, looky. This graph looks like it's continuous for all real numbers, doesn't it? Does it look like it's differentiable for all real numbers? No. Do you see a sharp turn anywhere? No, but why would it not be differentiable? What do you spy? No, not the flat part. The vertical flat, right? The vertical line. Good. It appears that there's a vertical tangent line almost at where it crosses the x-axis. Now, if we were to take the derivative of this, we would know that it would not be differentiable everywhere, right? Because we're on cusp alert. There's a fractional exponent less than 1. So we know when we take the derivative, it's going to become negative. It's going to throw it down to the denominator. And now it looks like -2 is the value that would give us the 0 for that. And does that look like -2? Yep. So we know there's a vertical tangent right there. So this function is not differentiable. But right now, that's just a review question. The point I'm trying to make is, hey, from just this separable differential equation that was not a function of x, we were able to separate the variables, integrate both sides, and relocate C to get this nice cubic function. And now if I just know one point that satisfies it, I can generate its graph. Pretty awesome. All right, let's do the same thing for part B. That was part A. Here's part B. Now we're just going to say when y, or 4, you can do that as well, when y of 0 equals -2, colon. And if you don't have room doing it off to the right-hand side, you can do it underneath there. And what am I going to do? Let's color code that. I'll switch this to blue. Blue, blue, blue. Let's draw it first. It passed through the point 0, -2. That didn't switch. Right here. So it's going to do this, and it's going to do this. So I want to know what that equation is now. So all I got to do is plug it into my general solution again, right up here. So I'm not going to rewrite it because I can see it this time. So I'm going to get -2 equals the cube root of 0 plus c. And now I get -2 equals the cube root of c. And I cube both sides, and I get c equals -2 cubed is -8, right? -8. So y must equal, and then I just plug it back into the general solution. The cube root of x cubed minus 8. Well, I claim that having a minus under the radical will give me the bottom one. You think so? I hope so. If not, we all go home. X cubed, oops, x cubed, oops, oops, double oops. And then -8 raised to the 1/3 power. If you hit graph in the same window, you see the bottom one form. Pretty cool. See? There she is, right? And now let's do the last one here. We'll do it in green. Green shows up nicely. The particular solution that passes through the point 0, 0. Hey, that's known as the origin, right? And look, it certainly looks like a, what do we call that? Linear function. How could it be that all of the solutions are curvy, but the one that passes through the origin is no curvature at all? Well, let's see. The math should kind of tell us why it is. So we'll say part C. You could say at 0, 0, or for f of y of 0 equals 0. But now again, we go back to the general solution. We're going to get y equals 0. It's going to become the cube root of 0 cubed plus c. So I get 0 equals the cube root of c. And if I cube both sides, what's 0 cubed? 0. So, and now I plug that particular value of c back into the general solution, and I get y equals the cube root of x cubed plus 0. But hey, anything plus 0 is itself. So that's really just the cube root of x cubed with, hey, what is the cube root of x cubed? X. OMG. Is that kind of what the graph looks like? Yeah, that's what it looks like. So isn't that cool? So those are called separable differential equations. When you have a function, a derivative that is equal to something other than a function of x, whether it's a function of x and y or just y sometimes, we have to separate the variables. Get the y's and the dy's on the left, your x's and dx's on the right, integrate both sides, plus c, solve for y, get the general solution, and then at the end, once you find your general solution, you can plug in and find particular values of c. That encompasses the entire section, right? I could stop right there and go into the next section, but normally I would not. And today is not a normal day. It's Texas Independence Day, Texas. Yeehaw. It's also Ash Wednesday 2. Yesterday was Ash Wednesday 1. I don't know. It's his words, not mine. Ash Wednesday 2, like 2.0. Oh, it's the sequel. Yeah, from last year. Right. The sequel from last year. Okay. All right. So I'm not going to graph it anymore because that kind of gets into the next section. What we're going to focus on the rest of this section is just strictly solving it analytically. Ready? Analytically. Find the general and particular solutions to the separable differential equation, giving these two initial conditions. All right. So what do you notice about this? It's a first derivative, and it does have x's on the left-hand side, right? But There's also y. Yeah, which is our dependent variable. So I have to be able to separate the variables by some type of either multiplication or division. That's it. Well, here's what I know I'm going to have to do. I know I'm going to have to multiply both sides by dx. So when in doubt, just go ahead and multiply both sides by dx. Sometimes that does the trick. Does that do the trick here? No. How do I get rid of that y factor? Divide both sides by y. So it'll divide out on this side. And on the right side, instead of putting dy divided by y, it's better if you put it as 1 over y dy. Did that separate the variables? Yeah, I have y's and dy's on the left, x's and dx's on the right, so that's going to be a check. Once you separate the variables, then you can integrate both sides right there. It's kind of fun to slide that slender, sneaky integral symbol like a snake after the equal sign. All right, now it's time to BOTC. On the left, what is the antiderivative of 1 over y with respect to y? Natural log of absolute value of y. Yeah. Now, do we need a plus c on the dependent variable side now, after what I just said? No. You certainly can. I call it c sub 1, but that's just an extra step. So you don't need the plus c on the dependent variable side, sorry. And now this becomes 1/3 x cubed, and now plus c. We have to put plus c right away. What some people do is they don't put the plus c until they solve for y, and then they just put plus c at the end. That's not how we've ever done it, okay? This would probably be worth 3 checks on this line. This would be what I call a point party. You'd get like a check for the left side's integral. Oh, good question. Derivative of y with respect to x. The bottom is always your independent variable, which is the bottom. It's with respect to, and then y is always your dependent variable. It's in the top. So there you go. So that's a good question, because it's not always going to be y's and x. It could be like the derivative of p with respect to q. And if you have something like q squared plus q, you don't have to separate the variables. You can just go right to p equals 1/3 q plus 1/2 q squared plus c, right? It's easy. If you have just independent variables, you don't have to separate the variables. But if you had dp dq, dq equaling p squared plus p, is that equal to dp equals 1/3 p cubed plus 1/2 p squared? No, it's not, because we have our dependent variable. So we would have to separate the variables. This is our dependent variable. Now we're going to do a problem like that later on. It's a BC only topic, but the students get confused. Normally, if you see x's and y's on the right-hand side, you're like, oh, got to separate them. But if it's only a dependent variable on the right-hand side, students miss that sometimes. They just go straight to the power rule, okay? So anyway, if we wanted to separate those, we would have to factor that first and then divide through by both factors. So, okay, that was a great question. Great question. Any other questions before we proceed? All right, so now we have to do some algebra, and I have to peel back the layers on the left. So how do we unnatural log something? We e it, right? So on the left side, you get e to the natural log of blob, which is the blob. And on the right side, you get e to the 1/3 x cubed. And where's the plus c? Is it in the exponent or on the ground floor? It's in the exponent, right? It's moved to the exponent. Now, here's a fork in the road. Don't take this fork that I'm about to go on. How do you get rid of the absolute values and solve for y? It's kind of a sticking point here. If you leave it in the form that I have right there, when you drop the absolute values, all you got to do is put plus or minus in front of the other side. I don't know if y'all learned that in algebra 2, but we're basically saying that since we're taking the absolute value, whatever's on the right-hand side can be positive or negative, okay? And then from there, you get your general solutions, right? The plus or minus in front would have to be there, And then depending on which particular point you were given, you're going to have to self-select whether you want it to be positive or negative. Okay. This could be your general solution though. The problem is for a particular solution, you must pick. You must manually pick. Manually pick the plus or the minus. So it's not the way I want to go. So here's the way I want you to go. And it kind of gets rid of that whole problem. Before I get rid of the absolute values by putting plus or minus, let's just keep them there for one more line. I'm going to use a little tool, a little trick of exponents. Not a trick, it's a rule of exponents. E to the something plus something is the same as e to the first times e to the second. Would you agree? We're not used to going in that direction. We're used to going from the green to the blue. That was like pre-cal algebra 2. When you're multiplying and the bases are the same, you add the exponents, right? But if you have a sum of exponents, you can split them up into individual factors by giving them each their own base, okay? So verify it by going in this direction, but we're going to go in this direction. Now, we haven't solved for y yet. So E, which is the number 2.7 raised to the unknown constant, guess what? ShamWow C, Southwest Conference. ShamWow Shi. ShamWow Shi. So this is going to be a new and improved C. And I'm going to put it in the front. C times E to the 1/3 x cubed, which is also the same as x cubed thirds. All right. Now I'm going to show up here e to the C equals C. Let e to the C equal C. So I took a plus C in the exponent and I brought it to the ground floor and turned it into a constant multiple. Well, guess what? Now, since C is unknown, I can drop the absolute values and I don't need to put plus or minus in front because C itself could be positive or negative. That's the way you should learn to go. All right. Because now when you get particular solutions, the sign of C will come out in the wash. Okay. You don't have to worry about picking it manually. All right. So I'm going to copy this because I'm way too far over on the right. That's the one I'm going to use. And now I'm going to bring it over here. This is my general solution. It's the one that I prefer. I can generate as many solutions as I want now. And again, notice that it is solved for y as a function of x. That's what's special about the types of separable and differential equations we're doing. Our derivative might be a function of x and y, but we're always going to be able to solve the solution for y as a function of x, like we're used to seeing. All right, so now let's do part A. We'll say at the point 0, 1, colon, or for f of 0 equals 1, you get 1 equals C times e to the 0. Well, what is e to the 0? 1, right? So C equals 1. So the particular solution is y equals 1 times e to the 1/3 x cubed. And of course, we don't need the 1 there, so it's just 1/3 x cubed. Yeah, it's the bottom line. I don't want to box it. That's the particular solution. And I don't need to worry about if it's plus or minus. Now, at the end here, if you're not sure if it works, just re-plug in that point. When you plug in a 0 for x, do you get out a 1 for y? E to the 0 is positive 1. Yeah. Yeah. Okay. That's part A. Let's do part B now. Part B, I'm still going to use the same general solution. Maybe I'll just copy that, paste it over here. But look what happens now. If you look at the point, I'm plugging in a 0 and getting out a -2. At the point 0, -2, what do I get? I'll plug in. I get -2 equals C e to the 0. Once again. And now e to the 0 is still 1. So guess what C equals? -2. So the particular solution is y equals -2 e to the 1/3 x cubed. And notice in that one, there is a negative in the front. But I didn't have to worry about it because it just came out when I found the value of C. Once you solve for your general solution, C is locked in. Okay, no more ShamWow C once you establish the general solution. All right, if you want to say that here, we'll say it again. C is locked in once you find the general solution. Up until there, let it absorb, let it absorb. All right, so this is one of like two special problems where we manipulate the C quite a bit, and it turns in from a plus C at the very end when we first saw it, which is a vertical shift. It made its way all the way then to an exponent, back down to the ground floor as a multiplier, and now it becomes really an A value in our standard transformation form. Okay, so be mindful of that trick of splitting up exponents by giving them their own base and multiplying. All right, let's take a look from an actual AP question then. Okay, this was 1984, question 4, which meant it was no calculator, and I think this one was an all play, maybe not. It was definitely on the AB exam, okay? Actual question, actual level of difficulty, an oldie but a goodie, right? Let f be a function with f of 1 equals 4. So when you read that, you're like, okay, no objections from me. That's your initial condition alert, right? Initial condition alert. Now, again, this doesn't mean initial like t equals 0. It just means that it's some value that satisfies f. Such that for all points x, y on the graph of f, the slope is given by this. dy dx is 3x squared plus 1 over 2y. That's a differential equation, isn't it? Is it just independent variables on the right? Is it just x's on the right? No, I've got a y over there. So if you've got any dependent variables on that side, in this case, any y's, whatever this variable is in the numerator, as Diana was asking, if you have one of those guys on that side, you have to separate the variables. You gotta. Now, you could cross multiply again. So constant multiples, they can go on either side. Doesn't matter. Everything's going to end up on the right. So if you just want to multiply both sides, well, we're not quite there yet. I'm getting ahead of myself. Okay. Part A, find the slope of the graph at the point where x equals 1. Find the slope at x equals 1. Oh, so all I got to do is plug in a 1 for x into the derivative, right? Find the slope at 1, find the derivative at 1. But crap, in order to use this machine here, I need not just the x value at 1, but I also need the y value at 1. How in the heck am I supposed to find the y value at 1? Oh, they gifted it to me. It's 1, 4. So here's what I'm going to say. Notation, notation, notation. Because it's already solved for dy dx, we're going to use the Leibniz notation, and that's the evaluation bar. And then you put the ordered pair here. So it's at 1, 4. That's the preferred way. We're evaluating the derivative at, and instead of saying x equals, we write it as an ordered pair. And now we just plug in. We get 3 times 1 squared is 3 plus 1 all over 2 times 4. And if you want to stop there, that's fine. I'm going to keep going. This becomes 1/2. All right, so I don't even know what the original function looks like, do I? No idea. But I do know that at the point 1, 4, it's increasing, right? Not very fast. It's going up 1 for every 2 it's going to the right. Good to know. Good to know. All right, part B, write an equation for the tangent line to the graph at x equals 1 and use it to approximate f of 1.2. All right, there's 2 things to do here, right? First of all, write an equation on the tangent line at 1. At 1. So this is what we're calling our center of approximation. Okay, so what do we need for the equation of a tangent line? Point and a slope, or slope and a point, right? At x equals 1. Well, let's get our information in front of us. I know the point is the point 1, 4. And I know the slope is what? What's the slope at 1, 4? 1/2. I just found it in part A. Oh, it's like they're helping me to succeed by asking questions in this fashion, right? Find this, and then now that you have it, use it. Okay, so I'm going to give the equation of the tangent line a name. I like L of x. So L of x, the tangent line, is in Taylor form the y value plus the slope times x minus the x value. 1998 is looking pretty good so far, isn't it? Yeah, that's right, 3.7. And then now use it to approximate f of 1.2. Hey, guess what? I read the words approximate and or the word estimate, so I'm on squiggle alert, squiggle alert, squiggle alert. So now we'll say, okay, new column. So f of 1.2, what comes next, Ethan? Oh, geez. F of 1.2, oh, geez. Well, that's what I heard. You need to enunciate better, Ethan. Squiggles. L of 1.2. Don't distract others if you don't want to pay attention. Like, there you go. Like, you should not like be turning around. Equals, right? Equals. Now, if I plug it in, Taylor form is set up nicely to approximate values near the center of the approximation. So don't distribute. Don't feel like you're cleaning it up. We're plugging in a 1.2 for x minus 1. Now, if this was a free response question, right? So you wouldn't have to go anything past that. But let's go ahead and do so for comparison purposes. 1.2 minus 1 is 0.2. What's half of 0.2? 0.1. So this becomes 4.1. Now, if we knew the concavity of the function between 1 and 1.2, we could determine if that's an over and under, but we don't know anything about it, and it didn't ask us to find if that was an over and under approximation. So I'm not going to volunteer taking the second derivative using the Hody high rule implicitly. All right, so there you go. It's good enough. Now, if this was a BC question, the only difference was instead of using a tangent line approximation, it'll say use Euler's method with 2 or 3 number steps. And we'll do that later. Okay, it's pretty easy. So this was an AB question. Part C, find f of x by solving the separable differential equation with this initial condition. Okay, this is where the majority of the points come from. This is typically worth 5, sometimes 6 points. It tells you to solve the differential equation. It even tells you that it's separable. So here's what I'm going to do. I'm going to multiply both sides by dx. I know I have to do that. And that doesn't do it, right? So I have a y in the bottom. So how do I get rid of the y? Multiply both sides by y. So I get y dy equals 3x squared plus 1 over 2, yucky, yucky, gross, gross, dx. Now, if you stop there, you're going to be fine. Instead of dividing by 2, I might pull that 1/2 out front. But in this case, you know what I might do? Because that factor of 2 on the right side, it could go anywhere. It could stay on the right, or yeah, you could actually send it over with the 2y if you want. Now, would that be helpful here?
Yes.
Yeah, it actually helps with your antiderivative. Now, notice if you take the entire denominator away, the 3x squared plus 1 drops down on the floor, and now you need what around it that you didn't need before? You need embraces, right? Parentheses. You know, hug that dude. Now, that's the separation that we really like, although you would get the points above as well if you had it over 2. Now, we sneak in the what? Once you separate the variables, you
Sneak in those
integral symbols. Yeah. You integrate both sides, okay? What's the antiderivative of 2y with respect to y? 2 times 1/2 y squared, or just y squared, right? That's why it's nice having the 2 over there. If it were anything other than a 2, I probably would have left it on the right-hand side and just factored out 1/2. Do I need a plus c on the dependent variable side? No. And on this side, I just get, oh, look, x cubed plus x plus c. Plus c has to appear right away. Plus c has to appear right away. Again, that's going to be worth at least another 2 checks. One for both antiderivatives, one for putting plus c. All right, now we just have to solve for y. Now, when I solve for y, I'm taking the square root of both sides. What have y'all been told over and over and over again when you take the square root or fourth root or even root of something? Positive or negative? You think it's still on, plus or minus? Heck yeah. And now it's x cubed plus x, and guess where the plus c is? It's inside the radical. It's not outside, okay? And there's your general solution. Now, unlike up above where we had plus or minus with the e, and I told you not to go that route because you have to manually pick, there's really no algebraic way to absorb the plus or minus in front by bringing the c that's under the radical now as a term out front. So you're stuck with this one. This one is your general solution. So these are the two cases where you do end up with a plus or minus in front. And this one, you have to be a little bit more cautious when you do particular solutions, okay? You're going to have to choose your own sign for the particular solution, okay? All right, but that would get another check for finding the general solution. All right, now I need to plug in the 0.14. So I'm actually going to go from right to left here. I'm going to say at the point 1, 4, colon. And now I plug in a 4 for y, and I get plus or minus the square root of 1 cubed plus 1 plus c. And now I just got to solve for c. So I get 4 equals plus or minus the square root of 2 plus c. And how do I get rid of the radical? Square both sides. When I square both sides, what happens to the plus or minus? It goes away because positive squared, negative squared, both positive. So I get 16 equals 2 plus c, and c must equal 14. Yeah. Now you're going to get another check for using c, not for finding the right c, because depending on how much you ShamWow with c on the way to the general solution, you might get a different value of c, but in the end, it's going to come out to be the same answer. All right. And so now we can finally say, we'll plug that into our solution. So y must equal, leave a little space for the plus or minus, the square root of x cubed plus x, and then c was plus 14. Now, if you don't ever consider plus or minus, back in the day, you could have gotten lucky. But in today's day and age, yeah, you're not going to get lucky, I don't think. So I have to manually choose. Huh? Well, because you didn't put the minus there, you just had the plus for the general solution, and your particular solution might have been positive. So how do I know now whether to choose a positive or a negative? It goes back to this point here. When I plug in a 1, I have to get out a what type of 4? A positive 4. So just kind of check now. If I plugged in a 1 on the inside, I get 1 plus 1 is 2, 2 plus 14 is 16. In order to get a positive, when I take the square root of 16, I need it to be what in front? I need it to be positive. Yeah. So that's what I'm saying. That would be serendipity, because you actually don't get a check for the general solution. I misspoke. You'd only get a check for the particular solution, which happens to be positive. Okay. Yes. Oh, no, that's a good question. There's no other function besides this one. So you could call it y or f of x. Yeah. If you want to name it f of x, that's fine. Yeah, that's a good question. I probably should call it f of x, but I'm not gonna. All right. All right, and then here's the last part of what the question was. Use your solution from part C to find the exact value, not an approximate value. So now I'm just going to say f of 1.2 equals, and I'm going to plug it in to the particular solution that I just found. The square root of 1.2 cubed plus 1.2 plus 14, right? And would you go any further than that? Heck no. Now, for comparison purposes, let me go ahead and do that. It should be close to our linear approximation, right? It should be close to 4.1. So let's see if I can find it and show it on here. Oh, got to reload the ROM. Dang it. Those Russians keep sneaking in here and stealing my ROM. Well, poor, their economy is suffering so poorly, so badly that they can't afford their own right now. So
We gotta still do that.
1.2 cubed plus 1.2. Did y'all watch the State of the Union address last night?
No, it's not game. What happened? That's
Well,
my
there were
mom's
2
favorite.
points of interest. The crazy representative from Colorado, I forgot her name, starts with B, when he was trying to make his point about how the brave men and women that fight for our country are sometimes sent home in caskets draped with flags. She yelled out right there, "Yeah, and you did that to 13 of them." She said that and everyone looked at her, and he just kind of rolled with it. And then the very next thing out of his mouth, he was talking about his dead son, So it's kind of just not the right time to do that. But anyway, she's kind of kooky. And then the other thing that I got me is at the end, he's like, blah, 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 we're the greatest country. We can do this together. We're all one. God bless America and God bless the United States and God bless every one of you. And then he goes, and go get him. That's how he ended it. And I was like, was that just kind of like an attaboy to the entire United States? Go get him, right? Or was he like tacitly saying, go get him, as in Putin? I don't know. I called my son right away, and he's like at a watch party. He's like, Dad, I don't know. I'm looking at election results right now too. I can't talk. I'm like, all right. But I don't know. I know that wasn't on script, that wasn't on the teleprompter.
Next time you need to get questions for your son.
Go get him or go get him, America. I would have liked it if you, what?
Is that a new catchphrase?
Go get him, America, or go get him, America. There's a big difference, right? Now, anyway, back to this. The actual value is 4.114. Look at this. Stay with me here. The approximation we found up here was 4.1. If I compare that to the actual, which is a little bit bigger, that means my approximation was actually an under approximation. Look at this. Instead of knowing the concavity to determine if it's an over and under approximation, if I know it's an under approximation, that tells me something about the concavity, right? Yeah. So my solution curve should be concave what? Up, right? So f of x must be CC up on the interval from x equals 1 to 1.2. Okay. That's pretty cool. So what's nice about these separable differential equations is we can get an approximation, and then a lot of times we can actually find the particular solution. Now, last thing before the bell gets us, what would the particular solution be if the initial condition where f of 1 equals -4 instead of +4? Well, you would still pick up your general solution, right? You would still pick up your general solution, which was the plus or minus, and we would plug it in, and we would get -4 equals this. We'll say at the point 1 -4. Blah blah blah. You're still going to get c equals 14. Did you know that? Because when you square both sides, the -4 becomes positive. So you get the particular solution y equals, leave a space, x cubed plus x plus 14. And now, is that the particular solution we want? No, because now when I plug in a 1, I need to get out a -4, and now we have to manually select the negative solution. And that's what I'm saying. I added this part to this problem because it is not 1998 anymore. And in 2022, they're probably not going to allow you to get it right by serendipity. So if you have a problem like this, you still have the plus or minus on the general solution, but you have to manually choose whether you want it to be positive or negative for your final solution. And if it's the E version, you don't have to worry about it if you can adeptly bring that C down from the exponent and put it out front. Okay. So we'll spend another little bit of a day on this. There's some other interesting types of problems, like on example 4, and then a couple of more things here dealing with strict exponential. And then tomorrow will be the last day before. We'll talk a little bit about the test on Friday too. It's just 4.1 through 4.4. So I'm not going to throw in there like absolute max, absolute min, concavity, optimization, related rates, none of that stuff. Okay. Mainly numeric methods and integration.